All right, so any questions from last time? Everything clear? All right, so we were talking about this issue of energy, and so we did the sort of Newtonian estimate, and now we want to do the proper general relativity treatment. Okay, so let's talk about that. All right, so first of all, um, well, there's different ways of introducing it, but a good starting point is to just look at the Einstein equations. Okay, and lurking inside the Einstein equations, here's our energy momentum tensor. But we've said that when we talk about that as the energy momentum tensor, it's really just the energy momentum tensor of matter, of stuff. Okay, so it doesn't by itself carry the energy of gravity. This is just of the matter part of the theory. Okay, so for example, let's say familiar thing might be, let's say you have some gravitational waves in the universe that are just moving through the vacuum. They carry energy, but there's no T mu nu there. There's no, let's say it's through the vacuum, so there's no atoms and stuff. So the T mu nu is zero, but you shouldn't say there's no energy or energy density. So somehow this thing over here knows about the value of the energy density and the energy momentum tensor in a way, lurking inside of that somehow. And we can flesh this out by decomposing the G mu nu, the Einstein tensor, into linear and nonlinear pieces. So remember, the Einstein tensor is very nonlinear, right? It comes from some contractions of the Riemann tensor. Riemann tensor involves the Christoffel symbols, which are nonlinear, involves products of the Christoffel symbols. So it has nonlinear, it involves nonlinear functions of the little g mu nu, the metric. But we're going to separate it into linear, call that L, and nonlinear NL. Write that as follows. There's the linear and nonlinear. Okay, so by definition, this will involve just derivatives of g. That's it, no g squareds or anything like that. This can have all the g squareds, etc., inside of it. Okay, so I do this, and now I'm just going to plug that back in here and move this term to the other side. So then we get g mu nu linear is 8 pi g T mu nu, and I'm going to subtract this one. And just compensate the 8 pi g. Okay, now I'm not necessarily offering it as a proof, but I wish to argue that this thing here, this is the correct energy momentum tensor of the theory, where this piece is the matter piece, as we've discussed, and this piece is the bit from gravity. So let me try to give you some idea as to why that's the case. Okay, so there's an identity which you can check, which is that the partial derivative of this thing is zero. Regular old conservation. So it's a math identity. You don't need to know any physics. It's just a property of, if you were to write out what this thing is, I won't write out directly the full g mu nu. We'll write out g00, which will be related to energy density in a few minutes. But it turns out the g mu nu linear has 6 terms in it. They're all linear, but there are 6 ways you can contract the indices. And so it's a little bit messy. But nevertheless, it's a math identity that d mu, g mu nu linear is 0. Okay, so this looks exactly like a regular conservation law, right? So the real honest to goodness T mu nu of the theory So T mu nu, let's call it total, which I claim is this thing. The contribution from matter and a contribution from gravity, so it depends on the structure of the space-time through the Einstein tensor, or at least the nonlinear parts of it. This object, this combination, therefore obeys this same rule because they're equal to each other up to a prefactor. Okay, so this thing obeys d mu nu for 0, which is exactly what the energy momentum tensor has to do. Does that make sense? Right. Energy momentum tensor, we've described it from day one as the density, the local density associated with the local conservation of energy and momentum. Okay. So if you want to be fancy about it, there's a Noether current associated with translation symmetry in space and time. And we have to find out what that is. So we could laboriously start with, say, the action and go through the Noether procedure and derive that it equals that thing. I haven't gone through that procedure to derive it for you, but I'm suggesting it is this. And in fact, we can be certain that it's this because, in fact, there's no other two-index symmetric object that's conserved. There's only one thing that does that you can ever construct. So if you find one that does it, you have to have the right thing. Does that seem reasonable? Okay. So there we have it. All right. So now let's focus on the energy density, or the total energy density, including matter and gravity. Remember, the energy density was just related to T00, or is T00. So I can call it rho total. And then this is evidently T00 minus G00 over 8 pi G. So this is the thing we called rho. Okay, without any subscripts, rho in this course has always just been the rho of the matter sector, including radiation, even dark energy. And then I can just give that thing a name. That thing must be somehow rho of, say, I don't know, gravity. So that's our total. We're just identifying these pieces here. Okay, so somehow if you were to, I'm not going to write it explicitly, but if you were to write out the nonlinear parts of the Einstein tensor and plug it in here, you would have the full energy density, including gravity. So are there questions about this?
End up with the great linear and have some time statement which is linear or something is equal to n. The classical analog very kind of statement.
Classical analog. So the closest, if we put aside energy for a moment and just think about electromagnetism, this is like, all we're trying to do here is isolate the thing on one side, which in electromagnetism would be d mu f mu nu, the field strength, and on the other side put the charge density, the honest to goodness conserved charge density. Okay, now you asked about linear versus nonlinear. Electromagnetism is already linear, so I said, well, that was pretty trivial. So I'm answering it in an indirect way, but in the case of QCD, you may know, if you try to play the game of QCD, you have to play the exact same game. So in the case of QCD, you may know that the F mu nus are actually nonlinear because gluons can scatter off gluons, just like gravity is nonlinear. So if you write down the equations of QCD, they will look more like this, the way we normally write them down. There's some nonlinear stuff here inside of the F mu nu, and then there's the sources, the color currents. But from that, you don't directly see what the true conservation law is. If you want to see the true conservation law, you have to break up the F mu nu, the field strengths of QCD, the color fields, into their linear piece and their nonlinear piece. Okay, so there's something. And then you put it to the other side, And then that combination, which would be the quarks current and some current associated with the gluons, it's that combination that's the conserved current of the theory. So we do the same game in QCD. But yeah. But in, yeah, other questions? So anyway, these statements, however, are exact. So I'm not making any statement that our theory is, we're in a regime that's nearly linear or anything like that. It's just a mathematical operation that we can break this up. Even if this term happens to be very big, I can still do the separation formally. And the big deal is this identity up here, an exact statement. And by this reasoning, I can identify for you the full thing that's actually conserved in the regular sense. So because this is true, as we described a few lectures ago, rest assured the integral d3x of rho total, that's the conserved energy. And conserved, well, conserved if you have you're integrating over a system that contains everything that's relevant, as opposed to just a subsystem. Yeah.
So this identity about the linear heat, this artifact of the way that we separated it out, or is it just saying that it's always true?
It's always true. Yeah, it's always true. So it's a math identity. So I haven't written out for you the G mu nu linear. I'm not going to be able to remember it, okay? But G mu nu linear involves a bunch of stuff. So it'll involve things like, yeah, for example, it can involve something like box operator, or I don't know, d alpha acting on G mu nu. Well, if I lower the indices, G mu nu, stuff like this. So some derivatives acting on G, but there are many terms, some with pluses and some with minuses. There are 6 ways you can contract indices, right? So I could also write, like, I don't know, d mu, I don't know, d alpha, g mu alpha, things like this. There's a bunch of terms, there are 6 of them. And then when you hit it with this derivative here, you take a divergence of that, they all pairwise cancel completely out to 0. So it's just a math identity. It doesn't matter what G mu nu you hand me. You can hand me any crazy metric you like, and it all cancels out. And yeah, this is sometimes called Bianchi identity, or the linear version of the Bianchi identity. That's right. So it's all analogous to in electromagnetism. If I just state that for a minute. So in electromagnetism, the Maxwell equations would look like d mu f mu nu equals j nu. And similarly, this thing is identically conserved. So it's a math identity. This one's actually really easy to prove, or this one's a bit of work, that d mu f mu nu equals 0. The reason that's a simple identity is because f mu nu is anti-symmetric in its indices, but partial derivatives commute. So you have symmetric contracted with anti-symmetric is always 0. So that's compatible with d nu j nu equals 0, which is the conservation law. Okay. So left-hand side, you identify the thing that's identically conserved, and then you learn, if you didn't know it already, that that object on the right-hand side must be conserved on the equations of motion. The right-hand side is not identically conserved. It's conserved in an interesting way that J mu is conserved. And it's just as interesting that this object is conserved. You have to solve the Einstein equations or this won't be conserved. Does that make sense? This is an identity. This is because of the Einstein equations that's conserved. All right. Again, you could start with Noether, crank the handle, and you would discover the same thing. But that's a lot more work. All right. Okay, so now let's see where we're going with all this. Okay, so I can write the total energy. So I have some region of interest. We're going to make that the whole universe later. But imagine for now it's just some region, and I integrate over that region. I want to know the energy in that region. Okay. So I just integrate up this stuff. Then I could integrate up T00. There would be nothing wrong with doing that. Okay. That would be the energy of matter, kind of like the mc squared of stuff, if you will, if objects at rest. And then a correction from gravity. So this would be kind of similar to how last time we talked about there was energy of matter, and then there was some Newtonian energy associated with the system. Okay. This formula, believe it or not, collapses to the Newtonian formula if you're in the appropriate Newtonian weak field limit. But that's the full general relativity answer, is that expression. Okay, but so that's fine, and we're left with an integral. But now I want to use this fact that it's also equal to the linear version of the Einstein tensor. So there's an alternate way of writing it, which is d3x g00 linear over 8 pi g. Okay. Now this is interesting for the following reason. So I haven't written out the full g mu nu, but I do want to write out the full g00, just that component. It's elegant and relevant. Okay. So let me tell you, you can imagine computing g00. Right? We know the definition of g mu nu, right? It's all the Riemann tensors and blah, blah, blah. Just go to the first linear order in that expression. It's a bit of work, but if you do it, you'll find the following. It's 1/2. I'm going to use spatial indices here. di, gjj. Let's not worry about raising and lowering. Just put everything down, okay? I'm not doing anything fancy. Is that okay? Just spatial indices. Minus dj, gij. Okay, so gij is the spatial 3x3 matrix of g mu nu. So funnily enough, g00 only cares about the spatial parts of gij. Just so happens to work out like that, let's say. So there you go. It's a linear expression, as promised. Right? There's no g squareds, it's just g. And we know the Einstein tensor involves second derivatives. There you see there are second derivatives. They happen to all be spatial derivatives. And there's just some interesting combination of i's versus j's. So gjj, I mean the trace, that means, you know, g11 plus g22 plus g33. And this just happens to be some other combination of indices. Okay. Now this is very interesting because you'll notice this is some, if you like, divergence of some vector. So this thing here, I don't know, just call it, I don't know, vi, for lack of a better name. Okay. The j index you sum over 1, 2, 3. So it has no j index left over, but it has a residual I index. Okay. So once you get rid of j, it's some vector determined by derivatives of the metric. A vector field, if you like. And so the g00 involves di vi, or I could call that, I don't know, div v, if you will. A half is not important. You absorb the half into what I call v, it doesn't matter. Okay? There's some kind of divergence. Maybe that will remind you of something. In electromagnetism, charge density is the divergence of the electric field. This thing, up to some 8 pi g, remember this is the energy density, the total energy density. There's some 8 pi g factor. Okay. So in electromagnetism, charge density is the divergence of the electric field. In gravity, the total energy density is the divergence of some fields involving derivatives of the metric. Kind of the divergence of the gravitational field, if you like. Okay, so I plug that into here, and then I want to use the divergence theorem. Because I can, right? It's just going to be like Gauss's law. So we can write this, if this has a boundary, I don't know, S is this label for the surface, the boundary surface of our region, this can be written as integral d2s, 1 over, I guess, 16 pi g, some unit vector that points out, normal vector, n, and then this thing, di. Sorry, that's rho total. Yeah. I pushed the 8 pi g down appropriately. Oh, sorry. Now I've integrated, so this is the total energy, excuse me, E total. Is that all right? So we have an expression for the energy density, which happens to be a divergence. So I can use the divergence theorem and then express the energy of this region by an integral over the boundary of the region, d2s, two-dimensional boundary integral of this quantity. Okay, so this is the, if I go back to electromagnetism, this is the analog of the total charge, is the integral d2s ni ei by Gauss's law. Okay. So the source of these theories, these relativistic theories, their source, because the source of gravity is energy. And energy has a boundary representation in terms of the gravitational field, just as charge has a boundary representation in terms of the an integral of the electric field. So these theories are very clever. They both do that. There is something similar, actually, even Newtonian gravity. Maybe I'll just mention for a minute. Okay. Can anyone think how I might, is there some analogous statement in Newtonian gravity? That's for the source. The source is now mass for Newtonian gravity. Can you write mass as a boundary integral? You probably all know that you can, but maybe it was never made clear that you could. Let me just mention that for 1 minute, just as an aside. So if you do Newtonian gravity, you have the Poisson equation. All right, rho m, mass density. I'm not trying to be fancy. Good old mass density, not energy density. And so therefore the mass of a region, the total mass, integral, right? Again, pick your region. I want to know the total mass in that region. I just integrate over the mass density. That's perfectly fine. But I could also write it like this, as the Laplacian over 4 pi g. And the Laplacian is also the same thing as the divergence of the gradient. I'll write an n here for the Newton potential. Okay, so then I could use the divergence theorem and write this as d2s di phi n 1 over 4 pi g. Okay. So even Newtonian gravity, we can do this game, right? But only for mass, not for energy. So in each of these cases, the source amazingly has a boundary representation. In Newtonian physics, there's not a deep reason for this. In relativity, there is a deep reason for all that, but we're not getting into that here. But let's just say it's true, as you've seen. And so it's kind of interesting, right? You have two ways of figuring out, say, the mass of a region, right? I could go through, and there's stuff in here. I go through in every little box, d3x, I compute the mass, and then I add it all up, and I do a volume's worth of integral. And that's perfectly fine. That's what this says to do. Nothing wrong with that. But this tells us there's another way of figuring out what the total mass in this region is. is that I go through and I measure the gravitational field, d phi, which is related to the acceleration or minus the acceleration of a test particle here. I measure the acceleration of a test particle, or grad phi, on this boundary and add it all up and only do 2 dimensions worth of work, 2D integral, and it computes for me the enclosed mass. Right? And famously, we all know that in electromagnetism, we can do the same game with the electric field. If I want to know the total charge in this region, I either add up all the little bits of charges that I count all the electrons and protons in here and so on and so forth and get the total charge. Right? That would be writing this as d3x rho charge density. Or I choose to instead just measure the electric field on the surface and do a surface integral, and I also compute the enclosed charge. That's Gauss's law for you. Okay? Now, we all used to talking about energy, and let's come back to energy. Right? We know about energy in Newtonian physics, energy in electromagnetism. But in those contexts, you can never write energy as a boundary integral, no matter how hard you try. You certainly can't bootstrap this to energy. You can't just put in a c squared and claim that's the energy. That won't know about the half mv squared energy of particles and so on and so forth. So there's no way there's a boundary representation for energy in Newtonian physics. I challenge you to try to construct one. It won't work. Nor is there a boundary representation for energy in pure electromagnetism, ignoring gravity. Right? So we have not boundary representation for charge, but that doesn't do you any good for energy. So for example, you know, the energy in electromagnetism, you might write as d3x, say 1/2 the electric field squared, 1/2 the magnetic field squared. Right? Those are expressions for the energy stored in the electric and magnetic fields. Okay? Units where epsilon naught and mu naught are equal to 1. And then there's some other stuff, right? The kinetic energy of the charges and so on that I'm not going to write out. Okay, these are the kind of things you would write. And it doesn't matter how hard you try, that thing is not a divergence, right? It's just a half e squared. Not the integral of the divergence of something, it's just that. Now, this lives its life as a good old 3D integral, and that's life, and that's fine. But when you say the word relativity and you say the word gravity, so this is relativistic, and you say the word gravity, then suddenly this new representation appears, a boundary representation for energy. Okay. So yes, this is a result of GR and GR alone. Let me also add that formula for energy, if you've never seen it before, is pretty amazing. That formula is exact. I didn't make any approximations. Okay, so to be clear, I don't mean that that's the formula for energy if you have a system where gravity is the most important thing, we can ignore other stuff like electrical energies and so on. No, that is the total energy of a system. So for example, maybe you're even just interested in a hydrogen atom. Okay, now the energies of a hydrogen atom, like the binding energy, minus 13.6 eV. And then there's the mc squared energy of the electron. And the nuclear energies inside of the proton and make up the mass of the proton, so on and so forth. That total energy of the hydrogen atom, we would normally compute it by doing things like this. Nothing to do with gravity, right? Gravity has almost no impact on the structure of a hydrogen atom, right? It's all about the electrical force and nuclei are associated with the strong force and so on. So you would do these kind of integrals. Nevertheless, that formula is still correct. So if you take a hydrogen atom, doesn't matter what's going on, and draw some surface around it, and you would measure the value of the metric on that surface and just take these derivatives, you just compute this boundary integral and it will output the energy of the hydrogen atom. It's the source of gravity. It's the way it works. Okay? And you will never see if you try to take the limit in which you ignore gravity, right? You better not be left with a boundary integral because we're not used to it. And that's what would happen. If you literally ignore gravity, you will be left with nothing. Because the limit in which you ignore gravity is the limit in which Gij becomes minus Kronecker delta Ij. It becomes the Minkowski -1, -1, -1. It becomes constants. So if you ignore gravity, you would say, oh, it's just Minkowski space. That means these derivatives are 0, so you get 0. But ignoring gravity means you also set G Newton to 0. Okay, so this expression would tell you the energy is 0 divided by 0. It'll tell you nothing. It won't be a contradiction. There is a nice energy for your hydrogen atom, but that thing won't be able to compute it for you. It would say 0 over 0 if you just boldly took that extreme limit and completely ignored gravity. But the moment you care about gravity, there's a finite formula, and it's thought to be exact. Okay, so questions about all this? All right. So now we wish to, but before we talk about cosmology, just one more comment. This kind of formula is often used, by the way, like if you have, like let's say you have some object here, like a neutron star or something, okay? And I want to know what's the total energy, or essentially the total mass of that neutron star. The usual thing of trying to do an integral over the energy, the regular energy, so to speak, and the gravitational energy, doing a kind of integral d3x throughout the interior of the neutron star is a perfectly valid thing to do, but it's basically no one knows how to do it. Because for that, even this bit, you wouldn't know how to integrate. Because we don't know a priori what is the energy density at the center of a neutron star, right? Some complicated quark, gluon, plasma, whatever's going on there. So we don't know the values of these things in their detail inside the neutron star. You can make estimates for it and so on, and that's fine, but we wouldn't know it exactly. On the other hand, you just draw a big surface surrounding this thing and measure what's going on with the metric out there, which you could imagine doing. So you never need to worry about the intricacies of what's going on inside if you're only interested in the total mass of that thing. So that's how you could just imagine doing this boundary integral. And so the way you can do those things in practice is you would compute the metric, which is relatively straightforward, so-called Schwarzschild metric out here, okay? And from that metric, it computes all sorts of things. If something comes nearby, it predicts how those things bend and so on. And then from that, you can actually measure the value of the Gij around this thing. We're not very good at measuring the Gij inside of it. And that's also equally difficult, but we don't need that. We just have to do an integral over some surface that houses this thing, the surface S. And that will compute the thing. And that energy, or the total mass effectively, up to some factor of c squared, is a big deal, right? When I say it's the conserved energy, that's what I mean. So for example, if this neutron star were to collapse to a black hole, and the black hole, say, has 30% less mass or less energy according to this formula, that 30% has to go somewhere because this is the conserved energy, right? So maybe 30% goes into its outer shell bouncing off and things like that, okay? Or if you apply this reasoning to, say, a pair of black holes that are orbiting each other, put some big surface around this thing, that's the total mass or energy of the system. Okay, if we're in the center of mass frame, we would use the phrase energy and mass interchangeably. And then when they merge, they tend to give you a new mass that's less, famously, like at LIGO observations. The new mass is less than the sum of the two. And that energy, according to this formula, has to be conserved and goes off somewhere, like into gravitational waves, and so forth. Okay, so anyway, it's not just some totally abstract thing. Any questions about this before we apply it to cosmology? If Gij is 0, is Minkowski, yeah, it's 0. That's right. Okay. Now I get your point. So there's a subtlety there in terms of, which in a way is sort of what I'm coming to. There's a question of order of limits in what you've described. So if I have a region here, if my region of interest is picked to be a fixed size, say 1 gigaparsec cubed or something. Let's say I fix the size of, I don't want to know what's the energy in that gigaparsec, okay? Now, if you go to the end of the universe, well, vacuum energy can change that. But if asymptotically we head towards Minkowski, this formula would predict that there's asymptotically zero energy in a gigaparsec cubed. Now, on the other hand, at any finite moment in time, maybe it's not exactly E equals zero, it's just a very small number, it's asymptoting to zero. But on the other hand, if you ask questions about, well, what's the energy of the whole universe, you may not just focus on 1 gigaparsec. You might say, well, the universe is getting bigger and bigger, so now you have an order of limits to worry about. And if the universe is infinite, you have to do an infinity times a very small number. Well, what do you end up with? There's a subtlety there. Does that make sense? Yeah. But yes, the energy density would be drifting towards zero unless it's dominated by vacuum energy, in which case it stays put. Okay. Now, in a way related to your point, I do want to talk now, okay, last time we discussed this issue that the energy of the universe looks to be changing. And that's to make things finite, I said, imagine the universe as the topology of a three-sphere. And then we can delete any infinities, right? They have a finite volume, and the energy was changing in time. Okay, but that was just the energy of matter, energy of non-gravitational stuff. Okay, so let's recall I don't know, matter versus time. We said when something like this, that was the radiation era, regular matter era, and then vacuum energy or whatever is going on with dark energy, okay? Time dependent. And I did not like that. And if it's on a three-sphere, this E is finite. It's a finite size universe, so we can take these limits rigorously. Okay, now remember this was E matter, and now our goal, we had a first little pass at the point, was to include Newton's estimate for the gravitational energy. Okay, it does reduce to Newton's formula in the weak field limit. Okay, but here's the exact answer from general relativity. Okay, so we want to then think about the total energy of the whole universe. Okay, so we have some big three-sphere. And we could talk about just the energy of a little patch. That's fine. But I'm interested in the energy of the whole thing. Right? It's only the energy of the whole system that should be conserved. Energy of subsystems are allowed to be non-conserved, right? So now, according to this formula, what do you think is the energy of this thing? Any takers? It's the energy of a three-sphere. What's the energy of the universe, assuming it has this topology of a three-sphere? Yeah. Somewhat negative. Maybe? Yeah? Zero. I always joke, whenever I ask questions, 50% of the time the answer is zero. But you are right. Why is it zero? Oh, so it's so it is my reasoning. 50% shot. Any reasons why it's zero? Let's think about what this is. So I have a region. I could do an integral over the volume of that region, the bulk of that region. Or we amazingly, thanks to GR, we can also compute it over the boundary of that region. So what's the boundary of a three-sphere? In your head, what's the boundary of a two-sphere? Yeah. Does not have a boundary, that's right. The boundary of a, picture our friend here, we can picture a two-sphere. There it is. And we're interested in the whole thing. So something that would have a boundary, for example, would be if you said, I only want to know what is the energy of, say, the northern hemisphere. Just say. So you could ask such a question. It's a valid question. What's the energy of the northern hemisphere? Well, it has a boundary, which is the equator. You're walking along your northern hemisphere, and then I'm at the edge of my manifold, which would be the equator. That's its boundary. And you would do this integral over the equator if you're interested in the energy just of one hemisphere. And you would get some number. And I can't say we compute it if we wanted to, if you assume FRW type of metric and so on, and we will get some answer. Okay. I can't claim that it's, like at this stage, I'm not totally sure if it's positive or negative. I suspect it's positive, because we know from Newton that the smaller the region is, you're dominated by the mc squared positive energy, and there's just a little bit of negative energy. Remember, even from Newton, the negative energy was getting bigger and bigger and bigger as we chose a bigger and bigger subregion. Okay, so you get out to the whole northern hemisphere, it's probably a little bit positive, I imagine. But now we keep on going. We make out, let me draw the boundary, as it were. So you make your boundary, you know, this little cap on the sphere. Right? So I integrate over all this bit, and I leave a little cap near the South Pole. Now that has a small boundary. You will get a small answer. And now you keep shrinking it down towards 0 because you're interested in integrating over the whole thing. Right? Whole integral over the whole thing is just computed by an integral over the boundary, which is shrunk to 0. So the integral is over the empty set now and must be 0. Okay? As long as there's not some horrible singularity or something, we're going to definitely get 0. Yeah, so that's the big deal. So I don't know, I'm going to plot this thing. E total is, what a great function, 0. And so it's conserved as it's 0 at every moment in time. Is that kind of interesting? So what we just said was the 3-sphere, any sphere, has no boundary. So this integral of this stuff must vanish. So this is the empty set, so to speak. Yeah, so somehow you can even see by this picture, somehow curvature is really playing a role, because it really mattered that I wrapped it all the way around the 3-sphere. Right? So intuitively, some curvature or some energy stored in gravity playing a really big role in this. Yeah. And yeah, if I just look at a little subregion where there are black holes and stars and whatnot, none of this works. You're just going to get some nice positive answer. I mean, it works, but it's not going to be 0. It's going to collapse to our usual thinking about energy for relatively small regions. Now, relatedly, since we're on this point, I put up electromagnetism to remind you of Gauss's law, okay, because it's a direct analogy. But we can actually literally learn something about electromagnetism too. Okay, so this formula for the charge, Gauss's law is still true, even if you have curved spacetime. This formula is still correct. Okay, so what can we say about the charge of the universe? 50% is, must be 100%. The charge must be 0 as well, right? So the charge also literally has a boundary representation. I should integrate the electric field over the boundary of the region. There's no boundary. By the exact same reasoning, if you're interested to know what might be the universe, the total charge is also 0. Okay? If we live on a 3-sphere. Now this secondary one, however, we can say it's the result of this neat little boundary formula, which is perfectly fine to say. There's also a good way of picturing why this must be 0 in the case of charge. Anyone have any other way of picturing why the charge must be 0 if our universe lives as the topology of a sphere? There's a way of picturing the electric field directly without saying the words boundary. Another word, I guess relatedly, the point that I'm making is that when you have, like, imagine this is your boundary, you have this tiny little boundary for a moment before we shrink it to 0. Okay, so the integral is an integral on that little circle down there. There's two ways of doing the integral. You can either do the integral of the interior of it, okay, or think of it as the other side, either way. So what do you think is going on with the electric field if you try to put an electric field on a sphere? Okay, so let's say somewhere here there's a plus charge. Okay, so if you put a plus on an electric field and you start drawing the electric field lines, okay, because it's a sphere, they have to go somewhere. Was there a? Yeah, they have to wrap around, they have to end somewhere. Right? What are they going to do? So you keep on drawing them. And then what do? They come over here and they meet. You can't do that. Electric field lines away from charges are continuous things. So I can't have them cross electric field lines. That doesn't make sense. It's just a well-defined vector at every point in space. So crossing is not allowed. Maybe they just run smoothly into each other, but that's a contradiction because this is going that way and this is going that way. So you can't have an electric field line that does that. So none of these things are allowed. Okay? So you cannot put electric field a net charge. The only get out of jail is that over here you have, say, a minus. And then this can come in and this can come in, and that's no problem. Okay? So you're allowed for every plus, there has to be a corresponding minus, and the net charge has to be 0. Yeah. That's right. Yeah. There should be no solutions. Yeah. So the net charge has to be 0, assuming you live on a 3-sphere. These arguments are not working if our universe is not topologically a sphere. Okay? For a topologically flat space or topologically hyperbolic, hyperboloid, okay, then this space just keeps on going forever and ever. We have some subtleties about, if I want to know the net energy, for example, I have to do some integral over this infinite thing. And there can be subtleties with how you take the limits and so on and so forth. So we can't have a direct argument that the energy should be 0. A bit more subtle. I think morally it should still be 0, but we don't know how to make that precise. But on a 3-sphere, we can precisely say it's 0, and that's good because we want the energy to be conserved. Yeah, so the net charge is also 0 by the same argument. And to be sure, this is compatible, let's say, with observations. It looks like the charge of our universe is 0. We don't know for sure, but looks like for every electron out there, there's another proton. And if our universe is a 3-sphere, that would explain, if you like, why that's the case. Okay? It had to be have a net charge of 0. All right. Now, on the topic of energy, how are we doing on time? On the topic of energy, the fact that the total energy is 0 also has some implications for thinking, even this as well, but perhaps especially this, has some thinking about, people talk about the Big Bang, the creation of the universe from nothing, things like that, okay, whatever that might mean. Imagine there's some state prior to this thing, whatever was going on in some weird prior state. You might imagine some very simple state that was nothing, so to speak, that had, for example, 0 energy, presumably 0 charge as well. Okay, if you have a state of 0 energy, and you thought this is the correct way that energy evolves, originally we just thought that was the answer. So here's the Big Bang. This is t is equal to 0, and this is it's actually some power law. It's growing and growing like 1 over t. Okay, so it's diverging, it seems. Okay, now maybe you cut it off somewhere. You don't go all the way to t is equal to 0. That may be a little too bold. You might say, something else is going on back there. But it still strikes one as being a little bit difficult to imagine how we started from nothing and then jumped to that big energy. Okay. The theory of inflation that we'll talk about later has something to say about that, where it kind of helps in a way, maybe changes the shape of that curve. But just at this level, we could say, gee whiz, I don't know how we're going to have such a giant energy that we start with out of nothing. But then when we include the energy of gravity, it's really was 0 all along. You can imagine this sort of bubble, this 3-sphere popped out. or some state of nothing in some way, and went from zero energy to zero energy. And there'll be no contradiction with the principle of energy conservation. Okay, and charge would certainly be compatible with that too. Questions about that? So it's intriguing that yeah, on a three sphere these things are zero. Was there a question?
Yeah.
Hmm.
You don't create energy out of nothing. There's no energy difference. Like chemistry, that's just one thing of the process. So why is that not happening all the time?
Well, yeah, so then there should be some, I guess, formula for the probability of these things to appear. And I can't hand you that formula right now, but I think the way it might play out is that these little bubbles that form might form one here and one there and one there. And it's not clear that the probability of forming, say you mean like in the universe now, the probability might be extremely small in that happening. But maybe in some extreme condition back here, the probability was whatever it needed to be, so it happened. Maybe it happened multiple times. There are many of these three spheres. We're living in one of them. But you would have to check whether your formula tells you that the probability of producing another three sphere in this room right now is big. And a theory that would have that as its answer would just be a wrong theory. But I think there exist theories where that's not the case. They can form in these extreme conditions, but not in the regular condition of this room. Yeah, I mean, remember, there's not just a matter of energy associated with this stuff. There are other things. You have to warp the space into a three sphere and so on. If you're starting with a small one, it's very warped, and that should suppress your probability of formation, so on and so forth. Perhaps. But I think you also have to work a little more that this three sphere, if it would appear in this room, to run this argument, we need, you have to then embed the three sphere into Minkowski space as well. So you have to think about the whole geometry. So maybe you imagine that if we have, because in this room is more or less Minkowski space. Okay, so there's your Minkowski space, and then you imagine somehow this three sphere pinching off or something. So you have to think about that type of structure. Okay, if it really pinches off, there's a separate three sphere that's topologically separated from us. It's disconnected from us if it's a true three sphere. Does that make sense? So you can ask about the probability of this thing that's connected to us, and then you can ask about the thing that's disconnected from us, the true three sphere. And you have to think about how we could even interact with that. So, I don't know, maybe there's a chance that it's happening and we can't see it. I don't know. But yeah, this is pretty involved stuff right now to make claims about that. All right. Okay, so in the remaining few minutes, I wanted to start a more proper discussion on dark energy, because we've been a bit glib about dark energy so far in the course. Well, just one other thing to say is that, intriguingly, as I said, the charge of the universe seems to be zero. The energy may be zero. There are other things in the universe that don't seem to be zero, like the net number of baryons in the universe, right? It looks like there's a pile of baryons, protons, and neutrons, and not many antiprotons, antineutrons. So there's a net charge of zero, but gigantic net baryon number, it would seem. But you can't, just to be clear, you can't run any of these arguments to declare that baryon number should be 0. It's of a completely different beast. So what's special about these things is that charge sources these fields, like electric field, and energy sources the gravitational field. Okay, and then there's a long story about the properties, special relativistic properties of those fields that allow you to construct these interesting formulas. But there isn't any, as far as we can tell, there's no field that's sourced by a baryon. Baryon's another source of some field. You would have heard about it by now, the baryon field or something we would have called it. As far as we know, that field doesn't exist. When those fields don't exist, you can't run any of these arguments, right? All you can do is say that the total number of baryons is the integral of the baryon density. That's all you can say. You can't re-express it in terms of derivatives of some associated field that it's supporting. Okay? So we have no argument, a priori, why the net baryon number should be 0. And we look out, and the net baryon number looks to be non-zero. It's all compatible with this. There's no contradiction. We might be surprised that the baryon number is big, and an initial universe maybe should have had 0 baryon number, but relatedly, we have no deep principle why baryon number should be conserved, unlike these things should be conserved. All right, maybe we can come back to that later. Okay, so far we assumed, all right, this is dE. We assumed that our dark energy, was the same thing as vacuum energy, or vacuum energy density. Okay. We don't know for sure that that's true. So let's talk about the first thing that we care about when we talk about dark energy, as you know, is that it's something to do with the acceleration of the universe. So we should talk about that a little bit more directly. And for that, it's useful to look at the second Friedmann equation. So A double dot over A minus 4 pi G over 3 rho plus 3P. We haven't used this equation much so far, but anyway, it's useful to look at it now. And so this A double dot is related to the acceleration, second derivative. If you want to be precise, you would say, if I'm interested in some object, say, I'm standing here at the center, and there's some other object, say some galaxy, I don't know, moving away. Remember, it's at a fixed x, but its physical separation, x physical, is the scale factor times the location of the galaxy. Okay, that's the physical separation to the galaxy. And so if you're interested in the acceleration, whether it's positive or negative, that's nothing other than x physical double dot, but this is just A double dot times the location of the galaxy, assuming the galaxy is just caught up in the flow of the universe. Okay? That's, again, remember, the beauty of co-moving coordinates. Co-moving coordinates, the galaxy is at a fixed x. Yeah, that's the co-moving one right there. All right, so anyway, the acceleration is therefore just controlled by A double dot up to some prefactor. Okay, so this is why we sort of loosely speak of this as acceleration, A double dot. But again, you should multiply it by the co-moving distance to the object of interest to convert it into a regular acceleration. All right, so if we look at this thing, right, normally we expect things to decelerate because of this minus sign here. Nothing other than the idea that gravity is attractive. So we expect things are moving out, things are attractive, so we expect things to slow down. And so it looks like that's exactly what this formula is saying. And indeed for matter, go back to the regular usage of the word matter, where the pressure is negligible, as we've discussed, or W of 0. This just says A double dot is minus 4 pi G over 3 rho. It's negative, so it's decelerating. That's the usual expectation. There's no radical change when it comes to radiation. pressure is 1/3 rho, right? W of a third. So now the acceleration maybe gets a factor of 2 difference, 8 pi g over 3 rho. You plug that into there. And so again, things are decelerating. And if I take vacuum energy for the moment, where pressure is minus rho, W of -1, you see this will flip the sign. I put P as minus rho, so I get some -2 here times a minus, so I get plus 8 pi g over 3. Okay, so we get acceleration. But we can talk a little more general than that, right? What is the condition for acceleration? It's just rho plus 3p is negative. Okay? Or if we assume that there's a simple equation of state, I just parameterize P as W rho, as we normally do, it's the statement that W is less than minus a third. Okay, so any material that has W less than minus a third, such as vacuum, which is -1, will lead to acceleration. Okay, as long as this thing becomes dominant. Right? It's no good if it's subdominant to the other components that will try to make it decelerate. Okay, so observations tell us that we have a universe that's currently accelerating. So if I was to plot for you this acceleration quantity a double dot versus time, it looks like a flip sign. Okay, so if I just sketch it very loosely, if I plot a double dot versus time, right? We know the past was matter and radiation domination. So these are all just negative quantities. And if you look at matter, the minus, there's rho. So rho was very big in the past, right? So this is some deep negative quantity here. Or I can normalize to A, doesn't matter too much. And then the idea is that at some point today, it's somehow positive. So it has to presumably cross like this. There was a special moment, we think, in the history of the universe where the acceleration went through 0 and then became positive. Right now, let's imagine possible values for W, okay, not assuming W is necessarily -1 for this dark energy. Okay, so we're going to consider it must obey W. Maybe I'll put a DE subscript on it. For dark energy, it should be less than minus a third to have any chance that it's going to have give us positive acceleration. And it could be -1. Okay, that would be vacuum. So let's consider some ranges for this thing. So if it's between -1 and minus a third, and we're interested in solving for the scale factor versus time, we already did that in this course. We solved for scale factor with some power law. Okay? So we already showed, we claim to have done it for any W, but there's some subtleties, that A of t was some power law 2/3, 1 plus W dark energy. You remember this formula? For any W, we initially just said, oh, any W, whatever it is, positive, negative, who cares? You get this. But we later, and this formula does work as long as W is bigger than -1. Okay, but we care about this range for acceleration. But we already described that if you make W too negative, this formula doesn't work anymore. And particularly when W is -1, remember this is no good, this is t to the infinity, and the correct solution was actually an exponential. Okay, let's put that in. Not less than, equal to. Then we also already showed A of t is some exponential, e to the, I don't know, h lambda t minus t naught. I write lambda. I guess I called it vacuum V. Okay, just some constant, Hubble. And now, something that, I don't know, maybe I'll get you to check on the homework. You can also ask the question, what if W is even more negative? What if it's less than -1, like -2 or something like that? So you can just go back to the Friedmann equation. Remember, all we're doing is integrating it up. And you can definitely integrate it up for any W. But as I said, if W gets to -1, you're already a bit of a subtlety. There's some log, and then you invert to get an exponential. And if it's even more negative than -1, you have to worry a bit about your limits of integration. You can't just blindly take the lower limit to 0. But anyway, you can show if W is less than -1, let's just say you can show, it's a bit of a funny form, it's a bit different. A of t looks like, again, t to this power, 2/3, 1 plus W dark energy. Maybe you can't just leave it like that. I'm going to put a brackets here. And there will be a prefactor. It depends on your conditions at some moment in the universe where your initial conditions for solving the differential equation. There's a minus sign and some t and some time scale, which is a parameter of the solution. And for lack of a better name, I'm going to call it t sub end, which is a parameter. Okay? And I wrote proportional to. You can put in your a naughts and your t naughts if you want. Is that okay? But here's a case where you cannot just, you can't arrange it so that a equals 0 at t is equal to 0 like you can here. It doesn't work that way. You can check with solving the differential equation. There's some subtlety with the limits of integration. Is that okay? But qualitatively, it's t to that power. And so now if we plot this stuff, and then we'll finish. So here's time. And here's the scale factor. So in the past, we had matter domination, right? So we know that, let's recall, A is proportional to t to the 2/3 for matter. So there's some matter like this. Let's just use that as a guide. The matter-only universe. And some radiation down here at early times, but some slowly increasing power. For different values of W, you have to hook it onto a late time dark energy era, and the shape is going to depend on the W. Okay, so for these W's here, it's going to transition to some new power law that looks like this. So it's going to follow the blue curve, it's going to look like matter, and then eventually some other power law. is minus a third less than W less than minus 1. And by the way, you should double check that if W is less than minus a third, the second derivative of this function is positive. So there's a point of inflection here somewhere where it's concave down and then it becomes concave up. Okay. If W is -1, it's an exponential. Okay, so actually it goes up. Let me maybe do a dash. And then it transitions, I don't know, to some exponential. So that rises somehow faster. Okay, I've got everything on top of each other here. And then finally, if you're in this regime where W is even more negative than -1, this exponent, by the way, here, this is a negative number, as you can see. So as t goes to Tn, this blows up, it diverges. Okay, so that final curve would be this one. It looks like matter for a while. Then it goes up, and then it diverges. And this time at which it diverges is what I'm calling T end. So in a finite amount of time, if W is less than -1, A runs off to infinity. That would be an interesting time to be around where the scale factor blows up. In a finite amount of time of your clock, the galaxies run infinitely far away from us if W is less than -1. Okay. All right, so we'll talk about this, I guess, next time. And so, but you can see by this picture, though, that for observations, you want to try to fit the observations to one of these curves. Okay, so imagine if the observations follow one of these curves, it gives you a clue that that's the correct value for W, for dark energy. And we'll go from there. And then I want to we'll tell you why it seems W of -1 is preferred, and then we'll talk more about the microscopic origin of vacuum energy. Okay, see you next week.